Welcome to this problem walkthrough. In today's session, we'll tackle LeetCode problem number 680, valid palindrome 2. We'll explore how to determine if a string can become a palindrome by removing at most one character. Let's dive in and break it down step by step. In this problem, we are working with palindromes, which are strings that read the same forward and backward. Your task is to determine if a given string can be made into a palindrome by deleting at most one character. The input is a single string S, where the length of S can range from 1 to 100,000 characters. The output will be a Boolean value, true if the string can become a palindrome with at most one deletion, and false if it cannot. For example, if the input string is ABA, it is already a palindrome, so the output would be true. This sets the stage for exploring more complex cases. Now, consider the example where the input string is ABCA. Here, by removing the character C, the remaining string ABA becomes a palindrome. Alternatively, removing B instead of C also results in the palindrome ACA. In either case, it's possible to achieve a palindrome with just one deletion, so the output is true. This highlights how we need to evaluate strings to determine if removing a single character can create symmetry around the center. For a string like ABC, the situation changes. Even if we remove one character, there is no way to rearrange or modify the string to make it a palindrome. Removing A leaves BC, removing B leaves AC, and removing C leaves AB, none of which are palindromes. Therefore, the output in this case would be false. Understanding this helps us see that not all strings can meet the condition with just one deletion, especially when the characters are too varied or asymmetrical. Finally, let's consider edge cases. For instance, a string with one character is always a palindrome, as it reads the same both forward and backward, so the output is always true. Similarly, if a string like racecars requires just one character, such as Z, to be removed to form racecar, it is still valid. However, for strings like ABCDEF, removing any one character still doesn't result in a palindrome. On the other hand, strings that are already palindromes, such as level, require no deletions, and the output would be true. These examples and constraints give you a comprehensive understanding of how to approach this problem logically and efficiently. To begin addressing this problem, we can consider the brute force approach. The idea here is straightforward. We systematically remove each character from the string one at a time and check if the resulting string is a palindrome. Essentially, this involves iterating through every index in the string, creating a new string with the character at that index removed, and then verifying whether the modified string is a palindrome. If removing any character produces a valid palindrome, we return true. Otherwise, if no such removal works, we return false. However, there's an important trade-off to consider. While this method is intuitive and easy to grasp, it's computationally expensive. Checking if a string is a palindrome takes linear time, and since we do this for each character in the string, the overall time complexity becomes quadratic, n squared. Additionally, we need to allocate space for creating a new string each time, leading to n space complexity. For longer strings, these repeated checks can make the approach inefficient and impractical. An optimized approach leverages the two-pointer technique to address these inefficiencies. Instead of blindly removing characters one by one, we use two pointers to systematically identify the problematic character, if any, that disrupts the palindrome structure. The two-pointer method works by placing one pointer at the start of the string and the other at the end. As long as the characters at these pointers match, we move both inward. If we encounter a mismatch, we test whether removing the left character or the right character resolves the issue. We do this by checking if either of the resulting substrings, after skipping one of the mismatched characters, forms a palindrome. This targeted approach avoids redundant work by focusing only on the problematic area of the string. By using a helper function to verify these substrings, we can efficiently determine whether the string can become a valid palindrome with at most one removal. The optimized two-pointer approach offers significant improvements in efficiency compared to the brute force method. Its time complexity is linear, n, because we traverse the string only once, and at most, perform one additional check for a substring. This makes it highly scalable for larger inputs. Furthermore, its space complexity is constant, 1, since no extra data structures are required apart from a few variables. While the two-pointer method is the preferred solution, it's worth noting an alternative approach, a recursive implementation of the same two-pointer logic. In this version, when a mismatch is detected, a recursive call is made to check if removing either the left or right character results in a palindrome. However, recursion introduces additional overhead due to stack space. Its time complexity remains O(n), but space complexity increases to O(n) because of the recursive call stack. This makes the recursive approach less practical for very large strings, where iterative methods are safer and more efficient. For this problem, the optimized two-pointer approach is the clear choice. It strikes the right balance between simplicity and efficiency, avoiding the brute force method's unnecessary redundancy and the recursion method's stack overhead. With its linear time complexity, O(n), and constant space complexity, O(1), this approach is both practical and performant. These attributes make it suitable not only for competitive programming but also for real-world applications where handling large strings efficiently is critical. By focusing on the minimal work required to validate the palindrome condition, the two-pointer technique ensures we solve the problem in an optimal manner. The problem requires us to determine if a given string can become a palindrome by removing at most one character. A palindrome is a string that reads the same forward and backward. To solve this, the brute force approach involves removing each character one by one and checking if the resulting string is a palindrome. This process can be broken into clear steps. First, iterate through all the characters of the string. For each character, remove it to form a new string using slicing. Then, check if the new string is a palindrome by comparing it to its reversed version. If any of these resulting strings is a palindrome, we return true. Otherwise, if no valid palindrome is found after removing each character, we return false. While simple, this approach involves creating multiple substrings and checking each one, which can be computationally expensive. The brute force approach, while conceptually straightforward, has a time complexity of O(n cubed). This is because removing a character and checking if the string is a palindrome involves slicing and reversing, both of which take O(n). Repeating this process for all n characters results in O(n cubed) complexity. To improve efficiency, the optimized approach eliminates the need to explicitly create substrings. Instead, we use a two-pointer technique to check if the string is a palindrome while allowing for one mismatch. The method starts by initializing two pointers at the start and end of the string. As long as the characters at both pointers match, we move the pointers inward. When a mismatch occurs, there are two options: either skip the left character and check the substring from the next left index to the current right index, or skip the right character and check the substring from the current left index to the previous right index. If either substring is a palindrome, we return true. If no mismatch is found, or if neither option results in a palindrome, we return false. This approach avoids generating new substrings unnecessarily, making it more efficient. The optimized approach has a time complexity of O(n). This is because checking if a substring is a palindrome takes O(n), and we perform this operation at most once when a mismatch occurs. The key insight behind this optimization is the property of palindromes. A string is palindromic if characters at corresponding positions from the start and end match. By using the two-pointer technique, we can efficiently traverse the string while allowing for one mismatch. Instead of explicitly removing a character, we simulate this by skipping either the left or right character when encountering a mismatch. This eliminates the overhead of creating new substrings and reduces the overall complexity. In essence, this approach combines simplicity and efficiency, leveraging the inherent properties of palindromes to achieve significant optimization over brute force methods. The algorithm primarily relies on the input string and two pointers, making it highly space efficient. The string is processed in place using the two pointers, which traverse the string from both ends, eliminating the need for additional data structures. Several edge cases must be considered to ensure correctness. For example, an empty string is considered a valid palindrome, so we return true. Similarly, a single character string is always a palindrome. If the input string is already a palindrome, we can return true immediately without any removals. However, if there are multiple mismatches, removing just one character won't suffice, and we return false. The algorithm works seamlessly for both odd and even length strings, as the two-pointer method inherently adapts to the symmetry of the input. These considerations ensure the solution is robust and handles all possible input scenarios effectively. Let's walk through two examples to see the algorithm in action. For the input string APK, we initialize pointers at the start and end. The first comparison, A and A, matches, so we move inward. Next, we compare B and C, which do not match. At this point, we explore two cases, skipping B to check if C is a palindrome, or skipping C to check if B is a palindrome. Since one of these cases results in a valid palindrome, we return true. For the input ABC, the first comparison between A and C also results in a mismatch. Again, we consider two cases, removing A or C. Both cases leave us with substrings that are not palindromes. Therefore, we return false, as no single removal can make the string a palindrome. These examples illustrate how the two-pointer method efficiently determines the result without unnecessary computations. The provided code solves the problem of determining whether a string can become a palindrome after removing at most one character. Explanation. 1. Helper function is _palindrome. This nested function checks if a given substring is a palindrome. It uses Python slicing to reverse the substring and compares it with the original string. 2. Two-pointer approach. The left pointer starts at the beginning of the string, and the right pointer starts at the end. This setup is used to compare characters symmetrically. 3. Character mismatch. If the characters at left and right do not match, the function attempts to skip either. The character at left checks substring S, left right, or the character at right checks substring S, left +1 right +1. If either of these substrings is a palindrome, the original string can become a palindrome by removing one character, so the function returns true. 4. Increment pointers. If characters match, the left pointer is increment, and the right pointer is decrement to continue the comparison. 5. Success case. If the loop completes without finding a mismatch, the function returns true, indicating the string is already a palindrome or can become one without removing any characters. Edge cases. Strings that are already palindromes. Strings with only one character, always a palindrome. Strings where only one removal can make them a palindrome. Strings where no amount of removal can make them a palindrome. The algorithm runs in O(n) due to the two-pointer traversal and substring checks, making it efficient for large inputs. Here, we begin by defining the main method valid palindrome, which takes a string S as input and determines if it can become a palindrome by removing at most one character. Inside this method, we define a helper function called isPalindrome that checks whether a substring of S is a palindrome. The helper function uses a two-pointer approach, comparing characters from the start and end of the substring. If the characters mismatch at any point, the function immediately returns false, otherwise, it continues until the pointers meet or cross, confirming the substring is a palindrome. Next, we initialize two pointers, left and right, pointing to the start and end of the string respectively. These pointers allow us to traverse the string from both ends. We then enter a while loop that continues as long as left is less than right. Inside the loop, we first check if the characters at the left and right pointers are equal. If they are not, we return the result of calling isPalindrome twice, once by skipping the character at the left pointer and once by skipping the character at the right pointer. This ensures we explore both possibilities for removing one character to potentially form a palindrome. Finally, if the loop completes without encountering a mismatch, we return true, as this means the string is already a palindrome. This return statement ensures that the method handles cases where no characters need to be removed. Overall, this implementation efficiently checks for validity by combining the two-pointer technique with the flexibility to skip one character when necessary. The use of the helper function keeps the code clean and modular, making it easy to understand and maintain. Here, we start with the input string APK. Initially, we set two pointers, left at the start of the string, which is index 0, and right at the end of the string, which is index 3. The function is_palindrome is used to check if a substring is a palindrome by comparing it to its reverse. On the first iteration, we compare the characters at the left and right indices, which are both A. Since they match, we move the left pointer to index 1 and the right pointer to index 2. In the second iteration, we compare the characters B and C, which do not match. To resolve this mismatch, we try removing one character. First, we check the substring BC by excluding the right character. The is_palindrome function tells us that BC is not a palindrome. Next, we check the substring B by excluding the left character, and this time it is a palindrome. Therefore, removing the right character C makes the string a valid palindrome, so the result is true. Now, let's analyze the input string racecar. As before, we initialize two pointers, left at index 0 and right at index 6. On the first iteration, the characters at these indices are both R. Since they match, we move the left pointer to index 1 and the right pointer to index 5. In the second iteration, we compare the characters at index 1 and index 5, and again, they match. We continue by incrementing left to index 2 and decrementing right to index 4. In the third iteration, the characters at these positions are both C, which are equal. At this point, we advance the left pointer to index 3 and the right pointer to index 3. Since the left pointer is now greater than or equal to the right pointer, we know the entire string has been checked and is a valid palindrome without needing any modifications. Therefore, the output is true. Finally, consider the input string ABCDF. We set up the left pointer at index 0 and the right pointer at index 5. On the first iteration, we compare the characters A and F, which do not match. To address the mismatch, we attempt to remove one character. First, we check the substring ABCDE by excluding the right character F. Using the is_palindrome function, we find that ABCDE is not a palindrome. Next, we check the substring BCDF by excluding the left character A, and again, it is not a palindrome. Since neither removal results in a valid palindrome, we conclude that it is not possible to make ABCDF a palindrome by removing just one character. Thus, the result is false. The time complexity of our solution is driven by two key components, the while loop and the calls to the is_palindrome function. First, consider the while loop. It operates by simultaneously moving the left pointer forward and the right pointer backward, comparing characters as it goes. In the worst case, these two pointers will meet at the middle of the string, resulting in approximately n/2 iterations for a string of length n. This contributes O(n) to the time complexity since each iteration involves constant time operations. Now, when the loop detects a mismatch between characters, the is_palindrome function is triggered. This function checks whether the substring formed by removing either the left or the right character is a palindrome. This check involves reversing the substring, which takes O(m) time for a substring of length m. In the worst case, the length of this substring can be as large as the original string, or O(n). Thus, the is_palindrome function can contribute up to O(n) for each mismatch. Together, these components form the foundation of the algorithm's time complexity analysis. Since the algorithm makes at most two calls to the is_palindrome function, one for each potential character removal, the total time contribution from these calls is limited to O(n). When we combine this with the O(n) contribution from the while loop, the overall time complexity of the solution becomes O(n). Shifting to space complexity, the primary aspects to consider are the memory used for the input string, the slicing operation in is_palindrome, and the additional variables. The input string itself is not altered or duplicated, so it contributes O(n) space. The slicing operation sub:(:(-1) creates a reversed copy of the substring being checked, and the maximum space usage for this operation is also O(n), as the length of the substring can be at most the length of the input string. Finally, variables like left, right, and others are constant in size, contributing O(1) space. Together, these elements determine the space complexity of the algorithm. Taking all components into account, the overall space complexity of the algorithm is O(n). Comparing this to a brute force approach highlights the efficiency of our solution. A naive method would involve generating all possible substrings formed by removing one character from the input and checking each for being a palindrome. For a string of length n, there are O(n) such substrings, and checking each one takes O(n) time, resulting in an overall time complexity of O(n squared). By contrast, the optimized solution avoids generating substrings explicitly. Instead, it directly examines at most two substrings for palindromic properties during the mismatch handling. This optimization reduces the time complexity from O(n) squared to O(n), making it significantly more efficient. Analyzing the best, average, and worst cases gives further insight into the algorithm's performance. In the best case, the input string is already a palindrome. Here, the while loop completes its O(n) iterations without detecting a mismatch, and no calls to is_palindrome are made. As a result, both the time complexity and space complexity are O(n). In the worst case, the string requires checking two substrings of length up to O(n) using the is_palindrome function, in addition to the O(n) iterations of the while loop. Even in this situation, the time complexity remains O(n), and the space complexity is O(n) as well. This consistency across best and worst cases makes the algorithm robust and predictable in terms of resource usage. To solidify our understanding, we can mathematically prove the big O bounds for time and space complexity. For time complexity, the while loop performs O(n) iterations, with each iteration taking constant time. Additionally, the is_palindrome function is called at most twice, and each call involves reversing a substring of length up to O(n), resulting in O(n) for each call. Summing these contributions gives a total time complexity of O(n). For space complexity, the algorithm requires O(n) for storing the input string and up to O(n) for the slicing operation in the is_palindrome function. Adding these contributions results in an overall space complexity of O(n). This linear time and space complexity is a significant improvement over the brute force approach, demonstrating the efficiency of this optimized solution. When solving valid palindrome 2, there are several common mistakes to watch out for. First, not handling edge cases like an empty string or a single character string can lead to runtime errors, even though these cases are trivially palindromes. Always validate your inputs to cover these scenarios. Another frequent issue arises when characters at the start and end of the string mismatch. In such cases, you need to consider both possible removal options, removing the left character or the right character. Missing one of these options will lead to incorrect results. Additionally, in brute force implementations, inefficient string slicing is a trap. Operations like si plus si plus 1 create entirely new strings, which can become a performance bottleneck when repeated in loops. Instead, aim to work directly with indices to avoid this overhead. Lastly, errors in the palindrome check itself can occur. For example, forgetting to properly reverse the string or using manual, inefficient methods to compare characters can lead to bugs or poor performance. A concise and efficient helper function is key to avoiding these pitfalls. Now, let's consider the importance of analyzing constraints and input limits. For instance, if the string length can reach up to 10 to the power of 5, a brute force solution with O(n) squared, or worse time complexity will time out. This makes it critical to optimize your approach. A key pattern in this problem is the ability to verify the palindrome condition while allowing for a single modification. This naturally aligns well with the two-pointer approach, as it efficiently traverses the string from both ends. To optimize further, focus on reducing unnecessary operations, such as avoiding string slicing. Using indices to track substrings is a much more efficient approach. During interviews, it's also important to clarify how edge cases are handled, such as empty strings, single characters, or cases where the string is already a palindrome. Finally, be prepared to discuss trade-offs. While brute force methods may be easier to articulate, the two-pointer approach is faster and more scalable. Always lead with the optimized solution to make a strong impression. To deepen your understanding, it's helpful to explore related problems. For example, valid palindrome 2, the problem we're discussing, focuses on determining if a string can become a palindrome by removing at most one character. A simpler precursor to this is problem 125, valid palindrome, which tests basic palindrome checking skills. For a more advanced challenge, problem 5, longest palindromic substring, emphasizes finding the longest contiguous palindromic substring. This builds intuition about palindrome properties and efficient ways to handle them. Lastly, problem 516, longest palindromic subsequence, introduces dynamic programming concepts to find the longest palindromic subsequence, which is a valuable skill for tackling more complex variations of string-based problems. Studying these related problems will not only reinforce your understanding of palindromes but also prepare you for a broader range of coding challenges. There are multiple approaches to solving valid palindrome 2, each with its own trade-offs. The brute force approach involves removing each character in the string one by one and checking if the resulting string is a palindrome. While this method is simple to implement, its time complexity is n²*n, which makes it impractical for large inputs. A more efficient alternative is the optimized two-pointer approach. Here, you start with pointers at both ends of the string and move inward. If characters mismatch, you explore both removal options and recursively validate the remaining substring. This approach has a time complexity of n, as each character is processed at most twice. Although slightly more complex, it is significantly faster and well-suited for large inputs. Another option is the dynamic programming approach, which involves constructing a DP table to find the longest palindromic subsequence. If the difference between the string length and the longest palindromic subsequence is at most 1, the string qualifies. While this method has a time complexity of n², it's typically overkill for this problem but can be useful for understanding related concepts. Choosing the right approach depends on the problem constraints and the level of optimization required. Great job following along. To recap, we explored an efficient solution to the valid palindrome 2 problem using a two-pointer approach. Remember, mastering these techniques can make a big difference in solving string-related problems. Thanks for watching, see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!